Today, we're going to dig into a really fascinating and frankly costly engineering paradox. How is it that energy-saving LED lights are managing to destroy heavy-duty industrial switches, these things we call contactors, and causing them to fail, sometimes catastrophically? So this is the core question. It's a huge issue for facility managers and engineers. Picture this, a huge commercial parking lot, and suddenly the lights are stuck on permanently. The culprit, surprisingly enough, is the brand new low-power LED fixtures that were installed to save money. They're actually welding the contactors that control them shut. So what's the physics behind this bizarre failure?
All right, let's dive in. We'll start with the paradox itself. Then we'll unmask the real cause, an event called capacitive inrush. From there, we'll look at the physics of how a contactor actually welds shut, and most importantly, how to pick the right one so this doesn't happen. And finally, we'll wrap up by talking about the new kind of engineering mindset that's really needed for these modern lighting systems.
Okay, let's start with the problem itself. We're seeing this play out in big, large-scale applications, like commercial parking lots where you've got dozens, maybe hundreds of fixtures all switching on at the exact same time. The system gets designed based on the light's super low energy use, but the control gear, it's just failing. And this right here is the heart of the paradox. An engineer does the math, right? They calculate the total load of an LED circuit, they see the really low amperage, and they pick a contactor that has more than enough capacity. Or so they think. But then that very same contactor welds itself shut. That low steady-state current you see on the spec sheet is completely deceptive. It's hiding a very brief but incredibly powerful electrical event.
So what is this hidden event? Well, it's called capacitive inrush, and it is the absolute key to understanding this entire problem. To get it, we have to stop looking at the normal operation and instead focus on the very first few milliseconds when that switch is flipped.
Okay, so here's the technical term, capacitive inrush. See, unlike an old incandescent bulb, an LED fixture is a complex electronic device. It has a power supply, or what we call a driver, and that driver is full of capacitors that smooth and convert the power. When the light is off, those capacitors are just sitting there empty. The instant you turn it on, they demand to be filled, like right now. And in doing so, they draw this massive instantaneous surge of current that is orders of magnitude higher than the normal operating current. For just a split second, that LED driver basically looks like a dead short to the power line. This really lays it out clearly. On the left, you've got the steady-state current. That's the low amperage you see on the spec sheet, the number everyone designs for. But on the right, you have the capacitive inrush current, a huge, ultra-brief spike that only happens the moment you turn the lights on. Designing a system based only on that steady-state number while totally ignoring the inrush, well, that's the direct cause of these failures. And the scale of this spike is just mind-boggling. We're talking about a peak inrush current that can be 100 to 250 times greater than the fixture's normal operating current. Now, it only lasts for a few hundred microseconds, which is incredibly fast, but the energy delivered in that tiny instant is immense. And it's that energy that is so incredibly destructive to standard electrical contacts. So how does this brief but massive current spike physically destroy a big, robust mechanical switch? The failure happens in a crazy fast sequence of events that unfolds in literally less time than it takes to blink. Let's break down the mechanics millisecond by millisecond. Okay, so here's the failure sequence step by step. First, the contactor coil gets energized, and the contacts start to move towards each other to close the circuit. But here's the thing. They don't just close cleanly, they actually bounce, making and breaking contact multiple times in just a few milliseconds. It's during those tiny bounces that the massive capacitive inrush current jumps across the microscopic air gap, creating an intense electrical arc. This arc is so hot it actually melts the surface of the contacts. Then, as the bouncing stops and the contacts finally press together for good, that molten metal cools and solidifies, creating a permanent weld that fuses the switch shut. And this highlights a really critical distinction from what we see with traditional motor loads. See, motor contactors are designed to handle arcing that happens when the circuit is opened or broken. That kind of arcing gradually erodes the contacts over a long time. But with LEDs, it's completely different. They cause contact welding on startup when the circuit is closed or made. So the failure mode isn't a slow erosion, it's an instantaneous fusion. So all of this brings us to the solution. Clearly, we can't just select our components based on that simple steady-state amperage rating anymore. We have to specify a contactor that is purpose-built to survive the unique and violent demands of an LED's capacitive inrush. So when you're picking out a contactor for an LED lighting job, there are 4 key things to look for. First, make sure it is specifically rated for capacitive loads. Second, look for a NEMA 410 compliance rating. That's a standard that specifically tests for durability against these high inrush currents. Third, check the contact material. You want to see something like silver tin oxide, which is much more resistant to welding. And finally, look for a more robust mechanical design. Things like stronger springs that can handle these intense forces.
And this right here is probably the single most important takeaway for anyone specifying this gear. A standard motor-rated contactor, you'll often see it designated with an AC3 rating, is absolutely the wrong tool for this job. It's designed to suppress an arc on shutdown, not survive a massive inrush current on startup. If you use one in a modern LED lighting system, you are basically guaranteeing a premature failure. This all leads to a much bigger strategy. Solving this problem takes more than just one new component. It really requires a whole new engineering mindset. We have to start designing for the transient event, not just for the steady-state operation.
So here are a few key best practices to keep in mind. Always prioritize NEMA 410 certified components. If you absolutely have to use a general-purpose contactor, you have to derate it significantly. For really large circuits, use controllers that can stagger the startup of different lighting banks. That way you prevent all that inrush from hitting at once. And finally, a really smart move is to protect your sensitive digital controls by using a less expensive interposing relay, sometimes called a pilot relay, to do the actual work of closing that main contactor coil.
And we'll end with this central question, which is really what it all boils down to. As we keep replacing older, simpler analog loads with modern, sophisticated electronics, our whole engineering approach has to evolve with it. System reliability isn't just about steady-state performance anymore. It's about surviving that first violent millisecond of operation. You have to design for the transient. Thanks for watching.